Okay guys, so you had a homework due today, so I hope you have been working on it and use it as class material to study. I mean, for the last 2 weeks, for the last week plus this week, basically we're just been doing problems, no? Okay, preparing for the exam. So this is Thermodynamics. Today is 4/24/18, and this will be lectures, not really lecture, but just class 23rd. And the page for you guys is 126. Okay, so do you have questions about the homework? For once, I printed the solution, so we don't have to go and... Which one? 107. Yeah. So let's see. Let me first look at it, because if I see it can be on the exam, let's do it. If I see something that probably not gonna happen, I'd rather just do problems that will be type of the exam. No, 107.
Yeah.
Was this one from this set of the homework, or was from the other one?
This
This one. Okay, here it is. Let me look at the solution at it right now. If this could be, yeah, this could be on the exam. So let's do it, okay? So let's go to 107. Okay, so it looks like the figure's on the other page. So let me just do the figure, and then we can look at this. All right, so let me just do the figure over here. Is it better the other way around for me? I don't know. Yeah, it might be better the other way around for me. Okay, so I don't know what the problem is about, but I do the figure and then we figure it out. So problem 6107. So it looks like there is one pipe that is connected to two other pipes. So two pipes connected to one pipe. So the flows, so let's see, so there's one going in this way, two, and then everything comes out this way. So let's see, what do we know about D? We know D1 is 4 feet, the diameter. I'm guessing it is. V1 is 400 feet per minute, and the initial temperature is 80 degrees Fahrenheit. For the second one, they gave us the volumetric flow rate, which is AV, equal to 2000 cubic feet per minute. the velocity is 600 feet per minute, and the temperature is 40 degrees Fahrenheit. Okay, in this section right here, they say that there is insulation. So no idea what they say that, but what do you think it is? Basically, I will say there is no heat, no? All right? And then we know V3 is 400 feet per minute. So it looks like we need to find the temperature and the diameter. Okay, so let me read the problem. So figure 107 shows data for a portion of the ducting in a ventilation system operating at steady state. The ducts are well insulated and the pressure is nearly 1 atmosphere. So let's say P1, so P1 equal P2 equals P3, 1 atmosphere. Steady state. Okay, assuming ideal gas model with CP equal to 0.24 BTUs Alvin Rankine ideal gas, and ignoring kinetic and potential energy, determine the temperature of the air exit T3 at the exit and the exit diameter and the rate of entropy production within the duct. Okay. All right, so let's do this. Keep this for that figure because that figure is gonna have it all the time. So let's see. Okay, what I'm looking at is that we have all the data to find the mass flows through 1 and 2. Okay, so let's see. What is the general let's find out, okay? I don't know how to do this yet. So what is the expression for the mass flow? Is AV divided by specific volume, no? So, if they give us the, okay, so let's say then, M1 would be equal to what? A1, V1 divided by V1, no? Okay? So let's see, if we use the ideal gas model, what do we have? We have P1, V1, correct? Would be equal to what? RT, which would be RT1. So we know the temperature, so we can rewrite from over here, V1 is equal to what? RT1 divided by P1. And then, if we know the diameter, what would be the area? What would be A1? It would be pi d1 squared over what? 4. So if we combine all this stuff, what do we get? So it will be R T1 divided by P1 by D1 squared divided by 4 times V1. Is it anything simplifying here? So M1 will be equal to what? Nothing simplifies, but this will be equal to pi D1 squared P1 V1 If you were late, come see me at the end of class because I checked the attendance. So pi divided by what? 4 R T T1. Okay, and what is R? But is it air over here? Do they tell us it's air?
I believe so. I thought I saw the problem.
Oh, yeah, first word.
Air flows through.
That's what I
Oh yeah, assuming the ideal gas model for air. Okay, so it's air. Yeah, okay, good. So if it's air, what is R? Is R bar divided by the molar mass? And I have no idea what is R bar for English units. I know it's 8.314 for SI, but remember I gave you that page with the units, no, that you can use. So what is the gas constant for English units? I mean, I can probably figure it out. 1,545? Is that what it is?
We want
Yeah, but here, okay. What are we dealing over here with? We are dealing with pressures that will be in what? PSI. So RBF foot square. The diameter will be in feet. In feet now. So I think we need to deal with the one that will be foot LBF, no? So I think that's the 1,545. So let me put it over here. R bar for 1,545 is foot LBF divided by LB Rankine. Okay, and over here, what is M? 28.97. Oh, I already put it. Okay, we know that. Okay, so let's be careful over here. Let's see what happened for the values. So D1. So we keep everything in feet. You want to move that in feet, or yeah, we need to move it in. We need to leave it in feet, I think. So D1 is 4 feet. What is V1? 400 feet per minute. So it's fine, but if we do this, we're gonna get M in what units? Per minute, no? Okay, so it's fine. I don't know if we need them per second or not. We can leave it in a minute, okay? It's just a preference. Then we have T1. So I think those units are fine. T1 is, okay, 80 degrees Fahrenheit. we need to transform this into what? So how much would that be? Plus 460, no? 540? All right, so we have D1. Okay, what would be P1? What is 1 atmosphere in English units? What is it? Okay, so 14.7 lb in square. So we need to move that stuff to 14.7 lb in square. What do we need to do? 1 foot square will be what? 144 of 12 square. So what do we get?
2,116.8.
2,000?
2,116.8.
Okay, so if you substitute everything into the equation, what do you get for M1? I mean, this problem so far is not difficult, but heavy with units, no? Okay, guys, I could just look the solution and give it to you, but the whole idea is to make the problem with you, no? 369 pounds per minute. You get exactly 369 or 369 point something?
369.5.
Yeah. That's also what they have on the solution, okay?
Professor,
Yes.
are you sure that your molar mass or errors in the correct units?
It's the same decimal range.
Yes, because it's pound per pound mole. This, I mean, you say the R bar or the M? M is 28.97.
It's the same.
It's no matter what, it's going to be the same. That's not going to change. So now, let's see. What will be the molar mass 2 is AV2 divided by V2. So that one should be a little bit easier. Because AV2, okay, AV2 is given to us, as you see on the figure. And if we use PV equal RT, we have that V2 will be equal to what? R T2 divided by P2. So basically, the mass flow of second part will be A V2 divided by R T2 divided by P2. So M2 is equal to P2 AV2 divided by RT2. So if we do the units, AV2 is given to us under the form of 2,000 cubic feet per minute. T2 is 400 degree Fahrenheit, so how many Rankins? 520 Rankins. And then P2 is basically equals to P1. So you give me the value of 2,000, 1,016.8, no?
Should it be 500? Yeah, 500.
Oh, it's given to us?
Well, no, the degree should be 500, and it's not 520.
Oh, sorry, 500. Sorry for that. Yeah, plus 460, 500. Sorry for that. And the pressure will be 216.8 lbf foot square. So what do you find for M2? What do you get? What do you get for the mass flow 2? I mean, guys, this is just use the calculator, so.
158.7.
So let's say 158.8. Okay, so now, all right, all this stuff because we need to find T3. So in order to find T3, let's say this is the same as the insulation. Let's say this is our system. So for the system, let us write down what would be the first principle of thermodynamics. So it's Q dot plus work dot plus what is coming in over here will be what? M1, H1. Anything else coming in? M2, H2. Is it something coming out? M3, H3. Okay, so from the figure, since we have insulation, what should be the amount of heat transfer? Zero. Is this pipe doing any work? So basically over here, we need to solve for H3, so we'll have H3 will be equal to what? M1 H1 plus M2 H2 divided by M dot 3 H3.
We don't put the HG on the bottom.
Yeah, no.
Oh, no, it's 2. Yeah, sorry, M3. Yeah, I don't know what I'm thinking about. Trying to think the next step. So one thing, guys, I think is we know that amount of mass flow going in equal to amount of mass flow going out, no? So M3, so what do we have here? We have M1 plus M2 should be equal to what? M3, no? So really we could rewrite this expression as H3 equal to what? M1 H1 plus M2 H2 divided by M1 plus M2. Okay, so I see two different ways how to solve this problem. All right, so can we solve this problem with the H?
Sure.
We can solve this problem for the H. We solve for H3, then we go to the tables and solve for H3, no? For T, okay? In the book here, in the solution, they use another solution which is also correct. What did they do? They say that H, since we are dealing with air, so what is air? It's a substance that is ideal. So if it's ideal, what does that mean?
Doesn't change state.
It doesn't change state. So if it doesn't change state, then the entropy is basically equal to what? CP T. Yeah? So we could replace the H by the CPT, so then they get everything in function of the temperatures, and they solve for T3. So you want to do it the same way they do it on the solutions that I'm going to give you, or you want to do it using the H?
Whichever way you're going to put it to test.
I might not put it on the test. But if you do it on the test and you do one way or the other, it's fine. I'm not expecting one or the other.
Which way do you think is easier?
Let's do it without the table.
Personally, I don't like the table, so
Let's do it without the table.
I will do without tables, okay? Okay, so we can write down. No, you know, like you, I don't like the tables. So, what is this? Okay, so for ideal gas, we know that H is basically equal to CPT. So that then, let's say this equation here, let's say equation star, okay, this equation here, I put it here, so that equation star becomes what? CPT3 equal to M1 CPT1 plus M2 CPT2 divided by M1 plus M2. So this will simplify to what? T3 equal to, because you can cancel those CPs on each side, will be equal to M dot 1 T1 plus M dot 2 T2 divided by M1 plus M2. So if you do the numerical application, I mean, you have everything now. We just calculate M1, M2. What is T1 is also given to you. I mean, you have all the data. So what do you get? 528.
Using the tables, you get the same number, yeah, just quickly.
Yeah, I mean, I don't like tables. Okay, I can get rid of the tables. Okay, now we also need to solve for the diameter of the thick pipe. So how can we solve for that one? So we know M3, which is actually equal to what? M1 plus M2, no? So we know the value will be equal to what? A V3 divided by V3, so it will be equal to A3 V3 divided by yeah. RT over P, so it will be RT3 over P3. So basically we need to solve for A3. Okay, yeah, I put A3 already. So A3 would be equal to what? M3 RT3 divided by V3, no, divided by P3 V3, you're right. P3 V3, okay? And A3 is equal to what? By D3 squared over 4, so we have pi D3 squared over 4 equals to M3 RT3 divided by P3 V3. So you're gonna have D3 equals to what? 4 and dot 3 R T3 divided by pi P3 V3 and you take the square root of all that stuff. Okay, so you see I'm not that interested about values, no? If I see equations, it's fine with me. So over here, I think units should be okay because velocity is in feet per minute. P3 we know is the 2116.8. We know R, we know T3, we know pi. So I need to do a calculation. Okay, what is M3 to all this stuff? M3 is should be the whatever we had, the 369.5 plus the 158.8, no? 528.27. What did I have? 528.27, okay. This is basically M1 plus M2. So then R is the 1545 divided by 28.97 times the T3 is, we just calculated, 528 divided by pi divided by the 2116.8, and that also divided by the V3, which is 400, and you take the square root of all that stuff. Okay, guys, remember, I do this stuff so you practice. If you don't practice, you miss, no? Jolly. Okay. All right, so now what I need to find out is what is the entropy change throughout the system. So what is the increasing entropy equation? If you remember, there is the change of entropy with the environment, which will be the delta Q over T. Yeah, plus so total change of entropy, total, will be equal to one of the system, no? Okay, so in our case, since we have the insulation, what will be the change of the entropy with the surrounding? 0. So then at the end, the total change of entropy will be equal to what? M dot 1 times what? S1. Okay, it's not complicated. Plus M dot 2 times what? S2 plus what? Why minus? They all go in the same direction, no? So plus, if it was opposite direction, yes, but M3 S3. So we could leave it under this form or rewrite M3 in the function of M1 plus M2 and see what happens. Oh, I do. As here they put minus M3 as 3. Why would they put the minus? Oh, because leaving the control volume. What do we put on the equation here? Yeah, but
Also, it might be backwards for our class.
No, that should not change anything. What will be negative? Is it just because it's leaving? Okay, I might buy that one. So let's see. Let me do a figure here. So basically, you can say M1 is going in, M2 is going in, M3 is leaving. So let's say it will be positive, positive, negative. So that means that this sign here is negative. I'm not sure about that one.
Can't all be adding to the entropy.
Okay, but let me ask you a question. Okay, this is a good, it's a good problem. Okay, what happens? Let's say instead of having air on both sides, you have here, let's say, hot water and cold water. Okay, so here something comes with the entropy of hot water, something comes with the entropy of cold water. So when you combine both of them, it's still going to be some change of entropy here, no? So if you do minus,
Aren't we imagining that it's
you see what I mean? I mean, I can understand here, you know, going in and out, but what happens if you have two different substances coming on each side? So the fact of combining the two substances is also going to generate some entropy, no? You see what I mean? I'm not that sure that it's minus.
Even if you had two substances coming in with the part that's leaving, it'd still be negative. It would be removed
Yeah.
from the system.
But then you will say that the total entropy is whatever one comes in plus whatever comes out the other one minus the way they react to each other? Or would it be
No,
the
it'd be-
summation of the three of them?
The sum of the two coming in minus whatever's going out would be the change. Just like it is here.
Okay, so let's leave the minus for now, okay? But you see what I mean? I understand what I'm saying, but what I'm saying is that if there are two different substances, they're going to combine with each other. So that's going to create a change in entropy.
Okay.
And that's not S3.
Oh, I see what you're saying. So there'd be another fourth term.
There should be something there. Let's do one thing here. Don't write anything yet, okay? Let me just look at something here. So if I rewrite now this as M1 S1 plus M2 S2, I think this might clarify the stuff. Plus M1 plus, I think that this is going to give what you say here. If you do this, then what do we get? M1 S1 minus S3, that now will be the difference, plus M2 S2 minus S3. That makes more, I don't know why, but to me the equation that way makes more sense. Okay. Yeah, it's negative. It is negative. All right. So now, this is the part that I've done, I think, 3 or 4 times. So this would be the fourth or the fifth time that I do it. So we are dealing with what type of system over here? Closed or open? Open. Do we have to care about the internal energy or the enthalpy? Enthalpy, okay? So let me do it maybe in another color. So what would be the change of entropy over here? What would be the S? Can we find the S? From where do we find the S? Not really, because this is air. So remember, the S for the air is an S upper sub naught, no? Which is not good. But basically, okay, let's rederive. Let us derive everything from scratch again. So what do we have? We know the equation from the first principle of thermodynamics is this one, and then we know that the change in entropy is equal to what? Delta Q over T. So here we know that delta Q is a change of notation, is basically equal to Q is equal to TdS. So basically we are just rederiving the TdS relation. So that means that the equation above becomes what? TdS plus work equals du. So this is important. You need to know how to do this. Now, what is work? Minus PDV. So doing this, we get the first TdS relation, which is for closed system. TdS equals to du plus PDV. Okay? This is the TdS relation for closed systems. But here we are interested in open systems. So open systems deal with what? Enthalpy and not internal energy. So what is the relation? H equal to what? U plus PV. So if we take the derivative of H, that will be equal to what? Du plus PDV plus VDP. Now we're going to substitute this one over here. I start going a bit faster, guys. So basically we're going to get TdS equals to what? dH minus, yeah, the PDV minus VDP plus PDV, so the PDVs cancel out. So we get the second TdS relation, which is for open systems. TdS equals to dH minus V dP. So next, for an ideal substance, what do we know about dH? It's basically equal to Cp dt. And if we use the ideal gas relation, PV equal RT, let's do it again. V will be equal to what? RT over P. So that means that the TdS relation becomes what? TdS equals to Cp dt minus R times T divided by P. Okay, this is the fourth or fifth time we do this. This by now, okay, should start getting clear, okay? So all this stuff, what I'm trying to do, why am I doing all this stuff? Because we're trying to solve for what? For ds, which is the change in entropy, no? So now, what can I do? I can divide everything by t, or move the t to the other side. So if I move the t to the other side, or I divide both sides by t, so I divide both sides by t, what do I get? ds will be equal to what? Cp dt over t minus r dp over p. So now what can we do? We can integrate, so let's say this will be S1, S2, S initial, S final, T initial, T final, P initial, P final. What would you get? S final minus S initial will be equal to what? Since Cp is more or less constant for an ideal substance, you have the dt over t becomes log, and dp over p becomes log. So basically at the end we have a relation which is the change in entropy is equal to Cp log T final over T initial minus R log Actually, I just realized something. This is simplified even more. We could have done it at the beginning, but I just realized. Okay, what do you think, guys, I'm thinking of? The pressures are constant, no? So what does that mean then?
Add that second term.
This one becomes 0 because P initial equals P final, because P1 equals P2 equals P3, no? Log of 1 is 0. So really at the end we have that the change in entropy is equal to Cp log T final minus T initial. So where is the equation for the change of entropy? So I'll come here. So now combining above equation with the one we just used before, the total change in entropy equals to m dot 1 S3 minus S1 plus n dot 2 S1 minus S3, sorry, S1 minus S3, S2 minus S3. This becomes what? M dot 1 of Cp log T let me check. Is it T3 over T1 or T1 over T3? Let me So it will be T3 over S1. Yeah, T3 over T1 plus n dot 2 Cp log see what they've done here. T3 T1, yeah, I think it's the same thing. So I mean, I could combine some of this stuff, but I'll let you do the calculation. So be careful to, yeah, I mean, we have all the temperatures in Rankines, no? Make sure you keep the temperature in Rankines, and the Cp was given to us to be at the beginning of the problem, the 0.24. Of the BTUs per LB Rankine, so that should be okay, yeah. So my only hope is that you get something positive. I don't care about the value. So what was T3 for us at the end? What did we find for T3? 528, which is 460, which would be 68, so it would be a middle temperature. Okay. And keeping the pressure, D3 should be big then, should be big, yeah, that makes sense, yeah. So it was 4.73, no?
Yeah.
0 point? Positive? Okay, I don't care about the value, 0.73? I mean, here they have 0.084. What are you getting, guys?
I got you said 0.086, but or yeah, something like that.
Okay, which is what they get here with 0.084. So let's say 0.083, okay? Okay, guys, so one thing, which is I think the way they do it on the book, let me check here. Okay, yeah, you see? All right, I know it's a little bit different, but now, huh. Minus the one of the exit. Okay, so let me just rewrite it a bit differently over here. So this is the n, but let's say that the increase in entropy, no, we can leave it as it is. I think I don't want to complicate stuff, but we need to remember this, that here when we take the m, then it is correct that we need to make sure about, we need to be careful about the sign of the mass flow, no? If it's going in or out, which I didn't think before. Okay, so we need to be careful with this. Is that clear, okay? So we have about 10 minutes, so that's not going to be enough to do another problem. So guys, please for Thursday, come, study, look at the solution of the homework, and come with questions. Okay? Will be the study time. All right, so see you Thursday for the last class. You came late, yeah.
Yeah, I was
So
on
let
the
me-
phone with my bank because my account's frozen and they don't know why. It's awesome.